Hey class, in this module, we're going to talk about computer fundamentals. Okay. Now, computers, they have four specific things that they can do: input, processing, storage, and output. Now, an input is something that is given to the computer, so information that is given to the computer. So if we look over here on the left, I just circled this little box here. We're talking about sensors, mainly on vehicles. Okay, those are like your main inputs. They can come from the computer, they can come from a switch, they can come from you when you turn something on or off. But you're telling the computer some information, you're giving the computer some information. Then the computer is going to go ahead and process that information. Okay. Information comes in in the form of voltage or no voltage. So it's either voltage on or voltage off, and it's going to happen very fast. Remember, the speed of electricity is approximately 6.28 billion times per second. Okay, so once the information comes in from the input into the computer, it is processed. Some information, if it can be stored, such as like your seat memory, that's stored. Anything from your engine control module, your transmission control module, like shift patterns, how hard you are on the throttle or the brakes, that information can be stored. Then the other information that is not necessarily stored at the moment, that it will be used by the vehicle, is called the output. So the output, the information comes from the computer, goes to the outputs, and the outputs do the actuation. They do the action, so to say. For example, you lift your switch up to roll your window up. That's an input. Okay. And that would be your window switch. Because you are the one that's lifting the switch up to roll your window up. That information is sent through the network and goes into the computer. The computer will process that information and understand that the request is to roll the window up. Then the information will be sent to the actuator. In this case, it'd be the motor, the electric window motor. Then the window motor would go up. It would turn on the relay and the window would go up. Okay. To us, it happens very, very fast. Obviously, we don't understand what's going on behind it, or I shouldn't say we don't understand it. We don't see what's going on behind it, because from the point that you lift the window switch up to the point where the window is actually going up is milliseconds to us. So for us, it's not enough time for us to process it. For the computer, it's relatively slow because they can process way more information than that at any given time. That's just a simple input request, so it's not high priority, meaning it's not going to take too long to process, but it's also not going to it's not going to affect other modules as well. Okay, so that's just a very basic example. But again, our inputs are things or information that is given to the computer. The computer processes the information. It'll either decide to store the information or to use the information and send it to the output. And the output is the item that completes the action, so to say, of what was being requested. Okay. Some of these slides, they are in this PowerPoint, are really for you to look at and to understand. I'm not going to go over every single slide in detail, like this one. But take your time. The PowerPoint is available for you without any narration, so you can just look through the PowerPoint yourself whenever you like, and you can take notes off that without the narration to it. Okay, so it's available in both forms on Canvas. Now, the computer memory here. So we have a couple different types of memory. We have RAM, ROM, PROM, EEPROM, and EEPROM. Now, obviously, they do different things. RAM is probably the most common one that people know about because it's in our phones. Our phones have RAM in them. Our laptops have RAM in them. Our computer modules on cars have RAM in them. Random access memory basically means your temporary memory. What's going on right now on your computer, how much RAM you have will help you in determining how many windows you can have open on your desktop, so to say, or on your web browser. The more RAM you have, the more apps you can have open on your phone at any given time. So that's what RAM is. What's going on now. Read-only memory is more like the operating system type of memory. Okay. But also the operating system could be something like programmable read-only memory as well.
because you can't perform updates. So like our phones get updates every now and then, our laptops get updates. The computer modules on cars, they get updates every now and then too as well. Okay. The other ones are pretty self-explanatory, but again, you can read through these. If you want to research them, you're welcome to research them to get a little more information. Now, there's one acronym here I do want to cover, OBD2. I think I have mentioned this before, but I do want to mention it here as well. Onboard Diagnostics Generation 2. That's what OBD2 stands for. And all of the communication for us when we connect a scan tool is done through that connector. Okay. So if we want to um, program, reprogram, or update a module, we would have to go through that connector to be able to do it. So that's why it was listed here. Okay. And how it's connected to the EEPROM. All right. Let's continue on now. So next slide, the computer. So we're just talking about the brain. So the ECU, but within the ECU, the CPU, the actual computer chip itself is the brain of the computer. The way we measured it is in hertz. That's how we measure the speed of the computer. There's also how we measure the speed of computers and laptops and desktop computers as well. So it's the same thing. So we have computers, that you're probably looking at right now or using a computer to view this, even if it's in your phone, same thing, or on a tablet, same thing. They have processors inside of them. They have CPUs. Our cars have CPUs in each module as well. And the way they work, I mentioned this already, but they work through binary code, or also known as voltage on and voltage off, or zeros and ones. So zeros and ones. Zero basically means no voltage, one means voltage, and that's all it means. Okay. So our code, the computer code, the basic computer code that uses is on and off binary. Okay. And so voltage on, voltage off. And that's when the computer knows to do that. And obviously, it's doing it extremely fast, multiple times in a certain pattern for a certain amount of time to be able to determine what the command is or what the input is. Okay. Variable resistors, we kind of went over this already. But if you want to look up more variable resistors, research the word potentiometer. Okay, so that's the word you're looking for, potentiometer, and that'll give you a little bit more information on variable resistors. But again, I don't want to go over that here just yet. Okay. Now, our analog wave, which is a sine wave. Now, computers work again on off signals and voltages. Now, voltage is going to be on, off, on, off, on, off. When we have an alternating current voltage, such as a wheel speed sensor, this line is right here in the middle. This is represents 0 volts. And this represents positive volts. And then this represents negative volts down here. Okay, and this line for negative, and this top line here for positive. Now, I noticed I didn't put a number on how much voltage because it can vary. It can be very small. It can only be 0.1, 0.2, zero point 0.3. It can be 10 volts. There's a difference, but the computer's not looking necessarily at how much voltage sometimes, all the time. It's looking at the variation of voltage, okay, as it goes up and down, up and down. And this is positive, negative, positive, negative. If we go back to magnetism, when electricity is generated, it is generated in this format, meaning it's an AC current, alternating current. So this is AC, alternating current. This is what the pattern looks like if we were to graph it. So it goes positive, negative, positive, negative. And the computer is not necessarily looking again on how much voltage, it's looking at the distances between. So if I have a distance between the peaks and the valleys, so here's our valleys at the bottom. What is the distance between here and how much time is given? Okay. Determining the time between those 2 points will determine, say, speed on a vehicle speed sensor. If we have less time between those 2 points, the vehicle is going faster. And that input will be given to the computer. The computer will process that input and then, put the number on your dash, for instance, as an example. Okay. So that's really what we're looking at. But this is a sine wave, and this is how alternating current is produced. And this is how alternating current is viewed, I should say. All right. We'll continue on. Computers use voltage as a signal for communication. We already talked about this. Again, that is binary, and that is zeros and ones, or voltage and no voltage. That's what we're looking at. Okay, voltage and no voltage. Now, engine mapping. Some of you may have heard the term of engine tuning. Engine mapping and tuning are relatively the same, or if not, they're relatively similar, if not the same things. Engine mapping is what's completed and done from the factory, meaning there's a computer program in your computer engine control module that tells the computer what to do at certain times, how much engine load is given, or how much engine load is applied, how much timing is needed, what the engine speed is, what the vehicle speed is, if you're going uphill or downhill, which is engine load, how good, what, if you're at altitude, if you're in the mountains, or if you're on flatland by the beach, if you're driving there, there's going to be different maps and different variations. Now, the engine map is going to be determined what the optimal conditions are for the engine to produce the least amount of emissions. Okay. It is not for the most power. There are maps for that, or programs, you can say. You can also think of an engine map as an engine program that can determine, you want the most power, then there's a map for that. If you want the least amount of pollution or emissions coming out of the tailpipe, there's a map for that. And that's what the manufacturer creates for the vehicles to reduce and to pollute the least amount. Okay. And then if you go and tune your engine and you want to make it faster, you go to a high performance shop to get it tuned, they're going to do the opposite. They're not going to care about emissions, and they're going to care about horsepower and torque, and they're going to increase the power. Okay. But again, we're still doing the same thing. We're reprogramming the computer to determine, when your ignition should spark, and how much fuel can be given into the engine, as far as how long the injector can be open, how much time. Okay. So there's various things we can do to increase power or reduce emissions. Right. And that's what engine mapping would do. Now, inputs, these are just examples of some inputs. There's way more inputs than this, but these are the most common ones that you'll see on most vehicles. ECT, which stands for engine coolant temperature sensor. MAP, which is manifold absolute pressure sensor, which is your vacuum. Think of like if you're going driving up a hill or driving down at sea level, that's going to change a lot. Okay, because there's much less pressure at altitude when you're high in the mountains. Your door lock switches, your window switches, which I kind of mentioned in the previous slides. IAT stands for intake air temperature. TPS stands for throttle position sensor, or APP, which is accelerator position, pedal position, accelerator pedal position. CKP is your crankshaft position sensor, and CMP is your camshaft position sensor. You also have sun sensors, and you have ambient temp sensors, meaning what's the temperature outside. The reason the car would want to know that is specifically for automatic temperature or automatic climate control systems, automatic AC systems. Okay. It needs to know what the temperature is outside and what the temperature is inside to be able to alter or adjust the doors that allow cold air to come in or hot air to come into the cabin where you're sitting. Okay. Again, and these are all inputs. They go into this is all information that is given to the module, then the module processes that information and then determines what is the best route after that. And we'll send it to the output to do something or store the information as needed. Okay. The main thing a computer can do with outputs. So now we're talking about outputs. Once it gets the information from the inputs, it goes in and processes it, then it sends it to an output. The examples of outputs are given here. Fuel injectors, transmission shift solenoids, AC compressor relay, fuel pump relay, throttle, motor. And this is just 5 examples, but there's more examples available. You can say your window regulator motor is an output, your door lock motors are an output. If you have an automatic tailgate, that is an output. So there's more outputs than listed here. But the output, what can be done is it can turn it off or on. Very simple. You either by giving an input to the computer can either turn the output on or turn it off. The one thing that's kind of not mentioned here too is we can turn it on, but it can be for a given amount of time. Okay. That's the one thing here. And that time is really related to the fuel injectors. So at idle, your fuel injectors are only on for very split seconds. So we're talking like maybe 3-4 milliseconds. When you want to go up a hill or you're taking off from a stop, they can be open for a longer period of time. They can be open for, say, maybe 15, 16, or 17 milliseconds. So it can also, it doesn't sound like a lot of time, but for a computer and for an engine, that's a long time. So that's triple the time at idle, so to say, about. Okay. So the injectors can be opened or closed. That's all the computer can do, but it can also do it for a certain amount of time. The longer the time, the more fuel that will be allowed to flow into the engine. Okay. And that's just one example of how outputs can work. This is just a little bit of terminology. So the term or the acronym PCM stands for Powertrain Control Module. That's a SAE term, which is Society of Automotive Engineers term that is used to identify the engine control module and transmission control module in one unit. Not all manufacturers use this. A lot of the early American manufacturers used to use this term a lot. A lot of them have gone away from it though. Now they have a separate engine control module and a separate transmission control module. But if you see the term or the acronym PCM, it's referring to the engine and the transmission together in one module. Okay, just so you know, so you're aware. Um, there are, again, these are more terminology too. Just so you know, the speed, how fast speed transmission is, how fast it goes, how it's rated is the baud rate. Okay, that's what it's called. Um, and then the voltage pulses. So we're looking at, like, say, how do I say time? Okay, how long the voltage is pulsing or how long the voltage is off. Okay, and that's just, these are just terminologies. So again, if you have, if you want to look these up, you can go look these terms up. But I'm just giving you this information just in case it's on a quiz or something, or you might see it in the book. Now here's a picture of a fuel pump motor and a PCM and a fuel pump relay. Okay. Just take your time, look at this, pause it here, or go look at the PowerPoint without the narration, and you can just identify where the motor is, where the PCM is, and how the electricity can flow. Again, this is a input output. Okay, our input is not shown here, but it would be your foot basically when you want to give it some gas and you need more fuel, or when you start the car, that's another input to start the car to turn the fuel pump relay on. Okay, then the relay is the output. All right. And as we're looking here, so we have a low side driver, we have a high side driver, fuel pump circuits. So now what we're talking about is the placement of the fuel pump motor in relation to the control module. So the control module can control a couple different things. It can control ground or control power. On the left side, the low side driver, this one, if you'll notice, you got to look at the diagram very carefully. But the PCM controls ground. Okay, you'll see within the PCM, you'll see a little symbol for ground. The PCM will control ground, so meaning that the power is always to the relay at all times. And when it wants to turn the relay on, it'll ground it. Okay, on the other side is the opposite. So at the high side driver, we have battery power. So we're controlling power to the relay. We're not controlling ground to the relay. Okay, different ways to wire things. The majority of things in your car are wired with the low side driver, meaning that the computers control ground. They do not control power. Okay, and that's how the majority of vehicles are wired. Now, duty cycle has to refer to the complete cycle of the on-off time. Okay, and it's measured in percentage. So how often, of the whole cycle, how much of it was it on and how much was it off? So if you look at the top one here, we have a true 50-50. So we're just looking at these lines here. I'm gonna draw them straight down. So we're just looking at the very, very first cycle, meaning from off to on, off to on. Okay, and that's our first cycle. Now, the top one is 50-50, meaning within that given period of time that we've identified within that cycle, it's on for 50% and it's off for 50%. So that's our 50% duty cycle. Now, the other one down below is on for 75% and off for 25%. So that's our 75% duty cycle. We could have the opposite too. where we only have 25% on and 75% off. Okay. So that's what we're looking, that's what we're talking about. How long is the circuit on for? Is it on for, of the cycle? We have to have an on and an off, and how long is it on within that cycle? Okay, that's exactly what we're looking at. All right. Again, if you want to look up more information, type in duty cycle for a vehicle, duty cycle for, say, a sensor or module, something like that, and something will come up and you can research it a little bit more. For this class, again, we're not going heavily into this. This would be covered more in a different class. Okay. We're just trying to get the basics down of computers and some different terminology. Now, in this one, okay, we're going to move on to networks and network systems. This might be a good time for you to take a break too, if needed. Okay. Now, computer communication is very similar to the computer communication that is done in your house, so to say, or at an office building, or on your cellular network. Your cellular network, your cell phone hits a cell tower, and then that cell tower is on a network. If you have, say, Verizon or T-Mobile or AT&T, it goes to that cell tower, then it goes to another cell tower, then it goes here, then it goes there, and then it's sent through the network before it gets to the actual person, right, that you're trying to text or call or whatever it is. Same thing in an office building. You may send some information to someone or send an email to someone. It goes through the network and then eventually gets to that person. If you send an email, depending on how busy the network and how big the network is, it may take a couple seconds. Sometimes it takes a minute or 2 minutes. I've seen it take a few minutes before. So because it's going through the network, it's moving through the network. So cars are the same way. Cars have networks. They have multiple computers on the vehicles, and the computers communicate with each other through the network. Okay. Not all computers communicate with each other. Some computers, or the majority of computers, will go to a central brain, sometimes called the central electronic module. Sometimes it's called the body control module. Different manufacturers have different names for it, but it'll go to the same brain, the same central module. Then the information will be sent out to the correct module who needs that information. Okay. The reason they do this is, it says right here, the reason they do this, reduce the amount of wires in the vehicle, okay, and shares data from sensors with different modules, okay. So we want to reduce wiring, and every time you reduce wiring in a vehicle, you save money when you're producing that vehicle. Because remember, vehicles are produced. We're talking millions of vehicles. We're not talking, a few hundred. We're talking millions of vehicles. If they can reduce, say, 500 feet of wiring in a vehicle, that's going to save the company and save the consumer a lot of money over the course of 1 million to 2 million, 5 million vehicles. So there's a big incentive to do that. Then also, we're reducing the amount of sensors we need in the vehicle. We only have one, say, engine coolant temperature sensor. So ECT. We only have one of those, and we only need one, because the sensor is going to tell the information that is needed to the engine control module. Then the engine control module can share it to the rest of the car if needed. Okay. We can have one sensor for, say, your door. If your door is not closed properly, there's one sensor for that. And then that can share information to the rest of the modules. It can share it to the dash. It can share it to the um, SRS, which is your airbag module. They can share it to the chime, to turn the chime on, the central electronic module or body control module. So there's one sensor, that sensor goes into a module, then that module can share it on the network with everyone else. So we don't need multiple sensors of everything. We need one sensor. And by doing this, this reduces the wiring in the vehicle that is needed too as well. Okay. So that's the reason why we have networks in vehicles. And networks in vehicles, I show the next, I think it's the next slide or one after that. Yeah, this one. So we have these modules and they're all in a loop, so to say. This picture only shows 4 modules. There's much more than that. But what this is referring to is we have one module communicating with the next, communicating with the next, and communicating with the next. So these modules are wired or shown in a circle like this. Sometimes they're shown in like a table, and the input from one sensor will go into one module, then that module will send it to the next one, then the next one, then the next one that's in a line. Maybe your vehicle speed mod input, say up here, okay, at this module, it doesn't need it. Who needs it is your ABS, which is over here, okay, which is over here in the bottom left. So what's going to do is going to take the input from the VSS, which is vehicle speed sensor. It's going to take that input information and send it to the next one. Your cruise control doesn't need it right now. It would eventually if you had it on. Your door module doesn't need it, but it's going to keep sending the signal and the information. But your ABS module wanted it. It was requesting it. It needed it. So it started up here. It went through two modules just to get to this one. Okay. Again, this is happening extremely fast, very fast. The speed of electricity, how fast electricity flows. Okay. And how fast these modules can process this information. But again, we only need the one vehicle speed sensor. We need the one module to collect that data. Then that data is put on the network and sent through the modules to the one module that is requesting it and needs it. Okay. And another term for this is multiplexing. But this is what vehicles do on cars, and this is why they're networked. Okay. So we can continue on here. Here's just another example of how they can be networked. If we look at them, we have our radio, we have our instrument cluster, and we have our heater, AC control. So these are all grouped into one group here, and we can get information going from and through modules. You see these, we have our junctions here. They can go through the radio or through one of these other modules to get to the PCM, or the PCM can send it back the other way and go through here. Okay, so there's different ways we can wire these. It's not wired in a circle in this instance. It's wired, with it looks like groups. But again, we can access this information through the DLC connector, data link connector, which is our OB2 connector, and it's located under the dash. That's a 16-pin connector. Okay, and we access all these modules through that connector on all vehicles. And again, there's just set up in a network where they can move through the information, can move through the modules as needed. If the certain module doesn't need that information, it'll just pass it along, basically. Okay. And here's another way to wire things. Okay. If you notice on the right side, we have our class C, and that's wired in like one big group. And then on the other left side, we have just the door modules, which are all wired in a group. And then we have some other different modules down here that are kind of wired in a group as well. Okay. So we can group them as well separately, all the modules. Okay, and just another example. The one thing I did not mention, which I do want to mention, is this word up here, CAN, or this acronym, I should say. Okay, controller. I'm gonna try and write this. I'm using my mouse, so it's gonna look kind of funny, but controller area network. Okay, so that's what CAN stands for. Controller area network. I know it looks kind of funny, but that's what it stands for. Okay. Controller area network. Now, our controller area network is the name for all this. The reason we use controller area network is because if you'll see these wires right here coming out of B plus and B minus, CAN minus, CAN plus, you'll see these wires and the way they're drawn. What it is, it's a twisted pair. So it's two wires that are twisted together. They're usually green and white in color, and they go to all the modules. That's just the network, how the modules communicate with each other. So our controller area network is identified by a positive and by a negative. So we have CAN C diagnostic plus, and then we have CAN C diagnostic minus. So negative and positive, because we have to have a positive and negative on everything. So that's how we identify it. And you can see the modules, all the modules have their own individual plus and minus. Okay. And we can have an A network, a B network, a C network, a D network. You can have as many networks as you want to have as required. Different manufacturers have more networks than others. I think lately, a lot of manufacturers are reducing the amount of networks they have because it just gets really complicated. So they can have less networks and maybe one big module that controls the majority of the networks, or controls the majority of the modules. And you only have maybe 2 or 3 networks instead of 20. Okay. Again, I don't want to get too deep into this, But this is, just your introduction to networking on vehicles and how computers are wired in our cars. Okay. All this stuff we would have to access through a scan tool. So you definitely would need a pretty good scan tool too that can communicate pretty rapidly and with a lot of the different modules in the vehicles. Not all scan tools can do this. So you need more, probably a more expensive scan tool for sure. Um, and if you work at a dealership or if you were to find a job at a dealership or get access to the dealer scan tool, then you would definitely be able to access all of them, all the modules. Okay. And maybe even perform updates and stuff like that too as well. The network, the controller area network does work off of voltages, and it's usually between 0 to 5 volts. It can go higher on some of them, but that's what we're looking at here, 0 to 5 volts for this specific type of network. There's different types of networks. You're going to see different acronyms for different networks, okay? I don't expect everyone to remember all of them. That's why the information is here for you, and you can always refer back to it, okay? And different manufacturers call them different things. But again, the voltages that we're using, so we're using on, off in this instance. So we're going 0 to 1, 0 to 1, 0 to 1, right? That's our binary code again. So no voltage, voltage, no voltage, voltage. But we're only going from 0 volts to 5 volts of the communication, okay? We don't have to go to 12 volts. There's no need to go to 12 volts for computers. We can stay within 5 volts. Most computers work off of 5 volts. Okay, if we can get everything done with 5 volts with less voltage than we can with 12 volts, and we can still have everything work the same, then let's just use less voltage. Puts less stress on everything. If we're using less voltage to get the same job done, it's going to put less stress on our battery and our alternator. And the rest of the network, we can have smaller wiring when we do this too and save money that way. So those are the reasons behind using 0 to 5 volts. Okay. Again, some do use 12 volts and some of the early systems did. This is again just pictures. I'm going to go through some of them. If you want to pause, you're more than welcome to pause and look over some of them. We don't really use this system anymore in modern vehicles, though. I don't know of any modern vehicles that use 0 to 12 volts for their communication network. Okay, there may be some that I'm not aware of, but I don't know any. And General Motors used 0 to 7 volts at one time. I don't think they do anymore. Some of their older vehicles would use that. And on the OBD2 connector, so the OBD2 connector, which is here, which I just circled, has 16 pins on it. Pin number 16 is power. Pin number 4 is ground. Pin number 6 is also, wait, sorry. I want to make sure I get the pin number 14, I believe is ground or communication. Anyways, we've talked about this before, and this is something you can look up really easily. So look up DLC connector, and then you can type in pins, and you can tell what they are. They can tell you what they are. I know 16 and 4; those are the common ones. There's a couple other common ones too. I think it's 6 and 14 that are common on all vehicles. But the the way we communicate is again through the DLC, which is the 16 pin connector, and different manufacturers will use different pins on the connector. Obviously, they can't use 4 16 because that's common through all vehicles. They can use any of the other ones they want. They can use 9 and 8 and 13 and 1, however they want. So General Motors decided to use pin number 2 for their communication network, which is class 2. This is an early system. You won't find it on modern GM vehicles, but some of the early ones you would find it on, say like in the early 2000s or even before that. And they would use 0 to 7 volts. Okay. Then this is again some of the early networking systems. And again, here's another one that used 12 volts. Again, UART, we don't really use this anymore, but you can look at this. You can go find the information on it if you like. Just showing you different examples. Yeah, here it is, 6 and 14. That's what I was trying to remember. So 6 and 14 are the high-speed CAN bus networks, and that's on all vehicles. Okay. Chassis ground is number 4, and power or 12 volts is number 16. Okay. Pin 16 and 14. PCM signal ground is pin number 5. All right. So these are just the terminals that are used on that OBD2 connector and what they're used for. All right. I don't expect you to remember them. I assume that most people are probably eventually going to remember 4 and 16 because those are the common ones that everyone checks and uses. the majority of the time. You'll probably also remember 5. So 4, 5, and 16. Those are the common ones that you're going to encounter a lot throughout, if you continue to work on vehicles or learn more about vehicles, you'll encounter those more so than you would any of the other ones. Okay, and again, I think I referred to twisted pair, but they're the two wires that are coming out of the CAN network, so positive and negative. Um, those are twisted. They're two wires that are physically twisted together. And the reason they do this is to cut out interference, reduce interference, because we're canceling out the two signals, and then the interference will be reduced by doing that. Okay, that's what it's referring to, twisted pair. To the physical wires are actually twisted. If you were to go to a wiring diagram or go into the wiring harness and look for them, you would see them. They're physically twisted together, just like this picture shows. Okay, some of this stuff is more for your quiz, and these items were used on vehicles that are really no longer in production, but it's just information just in case. If you're working on older vehicles or something like that, you may encounter this stuff. Okay, anything that's highlighted, go ahead and write it down. Ford OBD1, which we really don't use anymore, but if you're working on an older vehicle, just know that they did have basic data communication. Some of the early Fords did have that. Okay, and here's an example of it. Feel free to pause the video and look at it if you like. Same thing here. This is just identifying the Ford system that did use terminals 1 and 3 for your DLC. Okay, and this was OBD1, but uh, not common nowadays, but information is nice to have. Okay. And this is for the Ford system. It's just an example of the Ford system and how they worked. They use 2.5 volts for high, 2.5 volts for low, and then your 3.5 volts for when transmitting CAN high. The difference between CAN high and CAN low are speeds, or priority, I should say. The CAN high system is used for your engines, your brakes, your transmissions, stuff like that. Your CAN low system is used for, like, say, your radio, your driver's door, your passenger door, your air conditioning. If you notice that the high systems, the CAN high systems are higher priority, meaning they're more important, and the CAN low systems are not as important. I mean, I think we all think air conditioning and radio are important, but for the vehicle to actually work, they're not important at all. We can take those systems and remove them from the vehicle, and the vehicle will still work fine. So those are the difference between CAN high and CAN low, which is CAN H and CAN L. Okay, so you're aware of those. Again, take your time, look at these pictures if you like, go through them. These wires represent the twisted pair that I talked about. Okay. And again, different types of systems. There are terminating resistors in some of these systems, which are these. You'll see resistors right here. You have a 13K ohm resistor, you have a 120K ohm resistor, and you have another 13K ohm resistor. So different designs. There's a lot of different design and networks. No one's going to be an expert on all of them, but it's good to just see different variations of them. All right. Another one. A lot of these pictures, again, I just put in here for your information, FYI, kind of for you guys. So you guys are understanding and looking and, understanding that there's different types. Okay. Again, this system here uses a voltage that is between 0 and 5. So we have 0 volts down here and we have 5 volts way up here. It's not even shown on the graph, but the system is only going as low as 1.5 and as high as 3.5. See, so we can stay within, you don't have to go 0 all the way from 0 to 5, but you can go from 1.5 to 3.5 within that range. So you only have about a 3 voltage range to work with. Okay. And then the computers can, as long as they're designed that way, they would work fine. And the engineers are going to design it this way to understand, to make the computers understand what they're looking for. Okay. Another system that is designed, another different design of system that you can, look at here to get an example of everything. The DLC connector, which I've gone over. Again, a lot of repetition in this section of the course, is this section of the PowerPoint, but it's just trying to show you different examples. So, feel free to skip ahead or, pause as you need it, pause as needed. Okay. There are something called B codes and U codes. Now, the codes that you can get from any scan tool, Usually they have a P in front of them if they're their powertrain, a B for if they're for the body, or a U if they are for the network. Okay. So if you have a problem with the network, meaning the control area network that we've been discussing so far, if there's an issue with it, you can get a code that starts with a U. So if you ever see U and then 4 numbers after that, that's a network code. If you see a B and then 4 numbers after that, that is a body code. Something's wrong with in the interior of the body. If you see a P with 4 numbers after that, that's for your powertrain or your engine, so to say, or your transmission. Okay. Sorry, I skipped that one. Breakout boxes. This is a breakout box, also known as a Bob breakout box. These are just um, terminal extensions, so to say. You unplug the module, you plug the module into the breakout box, then you plug the breakout box back into the module. So it kind of makes like a path, like a series path, where you can check the connectors. So here, if we want to check voltage on any of these connectors, this is your OBD2 connector, 1 through 16. You can check voltage is relatively easy here. I mean, you could physically get down there and check it with a scan tool, but this just makes it way easier to do. Okay. And they have these available for different types of modules as well on all vehicles. They are very expensive and they're not easy to find, but they are available. If you work at a dealership, you would have better availability for them. These are some of the early connectors. So there's like OBD1 type of connector. This doesn't have a this may or may not, I should say, have a OBD2 connector. Okay, I'm not exactly sure because it's a BMW or Mercedes vehicles, but they do have their own manufacturer specific connector that can be accessed if you work at a dealership or if you have access to that type of scan tool. All right. And some of these, so I'm just giving you a different more example. So there's like a Honda scan tool. You can look up some of the Honda stuff, and some of this is an early system for sure. Um, and so I'm going to go ahead and just click through some of these. I don't want to get too in depth into these. Again, this would be covered more so in a more advanced class, but right now we're just trying to really cover the basics of communication and computers in a vehicle. All right. So we can end it with, so make sure, and again, anything that's highlighted, go ahead and write that down. That may be used on a quiz. Okay. And these are different types of networks here as well, but I'm going to end it, not on this one, but go ahead and if you want to pause here, this would be a good moment to pause and just look at the diagram and try to understand it. I'm going to leave it right here. Okay. The reason I'm going to leave it right here because this is a good example of the OBD2 connector and the different terminals on the connector. We've already talked about them, but go ahead and write the main 3 down, which is terminal number 4, terminal number 5, and terminal number 16. As you can see, here's your list of them and what they could be. The number 1, number 3, number 6, number 8, 9, and so on. They all say manufacturer's discretion, meaning the manufacturer, whoever made the car, they can put on there what they want. They can put on there their own data lines. They can make a different data line. Traditionally, most vehicles use 6 and 14 for data, but that's not always the case in all vehicles. So there's different manufacturers use that OBD2 connector in different ways. Okay. So hopefully you've learned a little bit about networks, communication, and computers and how they work on cars. Okay. If you have any questions, as always, feel free to reach out to me and contact me. Thank you very much.